Hello everybody and welcome to my 35th video. This is on the Quaternary SR and D type flip-flop. I'll be presenting the truth tables and the circuit diagrams for these flip-flops. Now first we can start with the SR flip-flop. Here we have the binary truth table for the SR flip-flop. S and R, Q for hold, 0, 0, 1 and not allowed, indeterminate state. So S equals 0, R equals 0 is a hold, S equals 0, R equals 1 is a reset with 0, S equals 1, R equals 0 is a set, which is 1, and S equals 1, R equals 1 is a don't care, a prohibited state. So here is the Quaternary SR truth table, inputs S and R and Q. And I've coded S, R and Q according to this table here. So if X is a quaternary logic 0, you get 0, 0, 0 for X3, X2, X1. If it's a 1, quaternary logic 1, 0, 0, 1. Quaternary logic 2, 0, 1, 1. And quaternary logic 3, 1, 1, 1. So S has been split into S1, S2, S3 according to this one, so is R and so is Q. Now I've chosen Q, the S and R values for Q to be S3 and R1, S3 and R1 for Q3. S2, Q2 sorry, is S2 and R2, S2 and R2, and Q1 is S1 and R3, S1 and R3. Why have I chosen this combination? Well, because it works. You could use other combinations, but they may not work. I've found that this combination works, so I'm going to stick with it. So for example, if S1 is a 1 and R1 is a 0, that's a set. This is Q1, that's a 1, which is a set. Alright, so these are the outputs of the Q truth table for Q, which, for example, 3, 0 is a set 3, 2, 1 is a set 2, 1, 2 is a set 1, and 0, 3 is a set 0. Now, once you've set your logic state, you need to get these values of S and R to 0, 0, which is the hold state Q. Q holds a 0, 1, 2 or 3. So, for example, set 3, R is already at 0, 3 goes to 2, 2, 0, which holds a 3, 3, Q could be a 0, 1 there, so 0, 1, 1 is a 2, and 1, 1, 1 is a 3, so you've got 2, 3. On its way down to 1, 1, 0, it holds a 3 there, and then to S equals 0, R equals 0, where it holds the logic 3 for Q. To set a logic 2, S is a 2, R is a 1, so I'm going to make life easy and set that to a 0 first, so you get 2, 0, which holds the logic 2, or 1, 0, which holds the logic 2, and then a 0, 0, which holds the logic 2. Just set a logic 1, S is a 1, R is a 2, so set R to 0 first, you get 0, 2, which is a logic 1, 0, 1, which is a logic 1, and 0, 0, which holds the logic 1, Q. And then to set a logic 0, S equals 0, R equals 3, and then S is already at 0, so you set R to 2, it holds the logic 0, R to 1 holds the logic 0, and you get 0, 0, which is Q, which holds the logic 0. So that's the truth table for the Quaternary SR flip-flop. So we can say that the quaternary function table for the SR flip-flop is as follows. If S equals 0 and R equals 0, Q equals Q, which is a hold. If S equals 0 and R equals 3, that's a reset, Q equals 0. S equals 1, R equals 2 is a set 1, Q equals 1. S equals 2, R equals 1 is a 2, set 2. S equals 3, R equals 0 is a set 3. Our Q is a 3. So this is the circuit diagram for the quaternary SR flip-flop. Here I've used the NAND configuration, which is not S, not R flip-flop. This is output Q. These are your set and R inputs. These are your outputs Q, not Q. And these are your set and reset inputs. So we have the quaternary S and the quaternary R here, the inputs. These are split into binary here, according to the previous table. So this is S3 here, SR1 there. This is S2 here, R2 there, S1 here, and R3 there. These are the outputs Q equals 0, 1, 2 or 3, and these outputs from the output resistors are connected together to form Q. This is the not Q. The not Q performs the value 3, 2, 1 in response to Q 0, 1, 2, 3, and these are the output resistors for not Q. The output impedance for the Q and not Q is a parallel combination of these resistors, so about 100 ohms for Q and 100 ohms for not Q. And that's it. Yeah, I'm using ACT00s for the NAND gates. These are NAND gates, and 74AT-T14s, which are hex Schmidt triggers to convert the quaternary into binary for S and R. Right. So this is the D-type flip-flop. Basically the operation of Q follows whatever input is D after the flip-flop has been clocked. So this is the input D, there's the output Q and not Q. This is the clock input. Again, quaternary to binary conversion here. This is input D2, this is input D1. These are 200 ohm resistors and 390 ohm resistors. So when you present a logic state to D, 0, 1, 2 or 3, it gets converted to binary. When you clock the flip-flop from a quaternary logic 1 to a quaternary logic 0, this clocks these D positive edge D flip-flops and stores the value of whatever it's at D2 and D1. It then gets presented to Q2 and Q1 and then converted from binary to quaternary for Q and in this not Q. Again, not Q performs the value 3210 in response to inputs of Q to outputs of Q to 0, 1, 2 and 3. So it's like an inverter. Right. I'm using, I've got an R, a not R and not S here. There, if R is a zero, it'll reset the flip-flop Q to 0. If S is a 0, it'll set the Q to a logic 3. Otherwise, these are set at logic 3s, quaternary logic 3s. Right, I think that concludes the video. Just like to say thanks for watching. I hope you enjoyed it. Bye.